Okay, let's start lecture number 11. We will start to talk about the radiation. At the same time, scattering and the diffraction. In rather unified way. The reason why I'm saying this is unified way will be addressed later on. Okay, radiation, a simple radiation problem. Is, as you saw before, one-dimensional case, when we have a wire, if it oscillates with the frequency of omega, obviously this oscillation will force the fluid to oscillate. Therefore, there will be some wave propagating into both directions. This is a very simple radiation. One of the important characteristics of this radiation is that the wave observed at any point with respect to this coordinate x can be expressed like P naught exponential minus j omega t minus kx or plus kx. And note that at any point the magnitude of pressure is constant. At any point the magnitude of pressure is constant. Okay, if we invite the concept of wavefront, okay, wavefront, which means that the surface or plane where the phase of a wave is constant. Okay, for example, if you look at the wave at this point, say x0, the wave front is constant. It does not depend on this direction. Okay? So essentially, this kind of wave does not have near field or far field concept. Because wavefront is constant and because the magnitude of acoustic wave is always constant, so everywhere wavefront is constant. So no far field or near field concept. That in terms of measurement point of view, you can put microphone anywhere, and you can measure it. So that is a very simple case. We do also understand that this case, this concept can be used for the case when we have war and when we have instant wave and reflected wave and transmitted wave. because this is equivalent with having blocked pressure, which is 2pi, plus radiation of the wall into both sides. Therefore, at chapter 3, I said the understanding radiation provide us to understand the, for example, partition problem. So let us expand what we understood about this to rather general case. Okay, suppose I have this kind of very irregular three-dimensional type of radiator, which would vibrate like this with a certain amplitude. This amplitude could be varied with respect to space. Then we would like to know how this kind of radiate in space. Obviously, the pressure field induced by this kind of radiation at arbitrary position and time would no longer be the form of like this. In other words, in the far field, it looked like, later on we will find out in the far field it looked like plane wave. In the near field, it exhibits more complicated form. So as we did always, to understand this kind of problem, this chapter will talk about the very simple radiator case. So let's start to see this problem by seeing one simple case, which is breathing sphere case. It's an interesting name because it uniformly breathing sphere. Therefore, all the fluid particles surrounding this sphere will move with the same phase. Okay. We may use now the velocity potential to describe this, and that can be has the form some amplitude divided by exponential minus j omega t minus k r in one dimension, because the wavefront at any position away from the center with a distance of r would be same, which we call, symmetric with respect to point. Okay? Then it should have this kind of form. The reason why you invite this velocity potential rather than using pressure field is because velocity potential is very useful, because the gradient of velocity potential will give us, for example, if I take a gradient of this velocity potential with respect to space, in this case, only dependency on space is with respect to r. This will give us the velocity in r direction. Okay, and also if I take a derivative of this velocity with respect to time, this will give me the pressure. Right? Does it give us the directly the pressure? So velocity potential is very useful in analytic or computational sense, because if you got this, taking a derivative with respect to certain direction, that will provide us the velocity in that direction. And if you take a derivative with respect to time, this potential function provides us pressure. So it's computationally very convenient, of course. That's why in old days, many people in acoustics use velocity potential and when they try to compute something which has interest. Okay. So we will start to see what's going to happen when we have this kind of simple or simplest radiator. And another simplest radiator would be the sphere, but it is oscillating in this direction. Therefore, in this case, the sound is radiating in both directions very effectively, but no sound radiation in this direction. It certainly gives us an idea what is the meaning of directivity and so on. So we will use that as a representative radiator. Okay, and later on, based on what we learned from these two cases, we will examine the radiation from baffled piston. In this case, we have a baffle, and the piston is oscillating with some frequency. We would like to know how this radiator produces the sound in space. Say if this is A or 2A, and then the wave is propagating like that, but some wave over this direction would have a smaller radiation efficiency, but you have a very strong radiation efficiency along this axis. Again, studying those kind of radiator, we could have more understanding about the radiation directivity. Having understanding this chapter expand the idea to this case. Okay, so because we do understand the radiation of this case, suppose we have a wall, we have an opening. If there is an instant wave coming in, then this part would be excited, and the fluid particle of that part excited, therefore it will have some velocity, then it will radiate. We will show how this understanding on this will be related to that. Okay, and then I move the problem to say there is a very long wall and no wall over there, and we will see how the wave will be diffracted by the presence of this kind of wall. Obviously, there will be very small radiation over here and some radiation to that direction. So I want to expand that understanding, this understanding, to this case. It's a half space case. And then I will invite what will be changing if I have a wall, if I have bottom over here. So by approaching the, what's going to happen in scattering, diffraction and radiation, using this simple case and that case, we can go to this rather complicated case. Therefore, I said this is sort of unified approach. What about the scattering? Okay, I have some scatterer. If there is an instant wave, then, as I said over here, the scattering problem we will see later is equal to the pressure due to the presence of this scatter that is similar with blocked frequency over there, plus the radiation due to this scatter. So if you understand the radiation, then we can understand the scattering too. Therefore, I can bravely say, if you understand the radiation of this breathing sphere and a trembling sphere, and next go to the radiation due to baffled piston, then you can establish the foundation of understanding to understand every radiation or physical phenomena of scattering diffraction problem. So this is a very important and essential foundation to understanding everything related with scattering and diffraction. Okay, let me demonstrate before I go into some of the details. Let me demonstrate some of the sound source. Okay, this is very well-known Korean jing, and which is not same as the Chinese gong. Okay. Okay, what you hear in the beginning is quite different to what you hear now. Let me demonstrate again. Okay, in the beginning, you can hear a lot of high frequency components. But now you can hear only very low frequency component. You may argue that, high frequency component means that oscillate fluid particle in very high frequency, therefore there are a lot of chance to lose energy compared with the low frequency case. But here again, and the radiated frequency content is changing in this case. This is a very typical and a very unique feature of Korean gong. In the beginning, because I hit the gong, I hit the jing with a large force, the jing is deflected, a large amount. And then later on, the deflection of the jing is getting smaller and smaller. So in the beginning, the stiffness of jing is considerably smaller than the stiffness of jing after having some enough time. So the vibration characteristic of jing is changing with respect to time. So this is a very typical nonlinear type radiation. And another feature you can hear, you can listen, you can experience from jing is that if I rotate this jing, then you can experience some case large sound, some case small sound. Okay? This case you will hear very large sound. This case you will hear a very small sound. It's because this instrument vibrates like that. Therefore, radiation in this axis would be very effective. But radiation in this direction is not effective, as the trembling sphere says. Right? So this is interesting. Because it radiates so powerfully, low frequency, it has been used as a very important musical instrument in older days, as well as in these days in the countryside. And this one is different one. And so maybe I will use this. Different sound. Okay. If I use this one, different sound. And then what you can experience is this one. It's different because this one excites more high frequency compared with this one, because contacting time of this one is wrong and the area is large. Therefore, the excited frequency is different. In this case, low frequency. In this case, high frequency. Okay, this kind of tempo you hear very much in old days in the countryside. Okay, another one. When I use hand over there, and I hit it, you will hear a different sound because you change the boundary condition. It's different, right? If you hold it, you observe sound, therefore there's no sound is radiating. Different sound because you excite a different way. So musical instrument is very interesting radiator. Okay, very interesting radiator. Okay. So I had enough entertainment for the students, so I can go to the some of the maybe painful but interesting theoretical study associated with breathing sphere first.